Good morning. So, let us start the next lecture of the subject operating system. So, today we are going to discuss the topic from the second unit, that is process description and control, that we are discussing. So, the first point we have discussed about the process control block, the different types of schedulers, long term as well as the short term schedulers, right? And we have also discussed the thread, that is process, thread, multi-threading model, the difference between the thread and the process, that we have already discussed. Now, the last topic from this unit that we are going to see today, and the name is scheduling. The very important topic with reference to process management, the scheduling is very much important concept. So here we have to discuss about the different types of scheduling, scheduling algorithms, and thread scheduling. Getting this point? So let us start with the concept CPU scheduling. So in the CPU scheduling, we are going to discuss about the basic concept, primitive scheduling, then the scheduling criteria. The criteria are CPU utilization, throughput, turnaround time, waiting time, response time, and the algorithms. The most importantly, the CPU scheduling algorithm, that is first come first serve, the shortest job first, the priority scheduling, round robin, and the multiple processor scheduling and the real-time scheduling that we have to see. Now, before actually starting the CPU scheduling, already we have discussed about the scheduling. What is the meaning of scheduling and why it is required? So again come to the concept that scheduling means what? The proper timetable or proper schedule for that particular event to occur, right? In case of multiprocessor architecture, as we know that there are n number of processes, they are running parallelly in the system. Concurrent execution of n number of processes are getting done in that particular operating system. So if we want to execute each process without any problem, if we want to execute each process without any hurdle, then there must be cooperation, or there must be some sequence, or there must be proper schedule to be given to each and every process. So process must be scheduled. So in case of multi-programming architecture, the several processes kept in the memory at a time, means they are kept in a ready queue. Now these processes, you know that these processes, they are ready for the execution. And when one process has to wait, operating system takes away CPU from that process and give it to the another process. So again, think of that our process state diagram. In the process state diagram, processes, there are 10 processes, they are now waiting. 10 processes, they are now in waiting in a ready queue. And out of these 10 processes, one process is to be selected and it is assigned to the processor for the execution. Clear? Now, when the process, suppose process P1 is given to the processor for the execution. Now, suppose if that particular process currently in a running state, and during after 50% of its execution, the process may require certain IO operations. Here, the process may require certain IO operation, right? So that process must be removed from the processor and it is placed inside the waiting state, or it is placed inside the different device queue, IO queue. You know it very well, right? So, and the processor immediately go for the next process. Processor immediately take the next process. Now, this particular part is handled by your CPU scheduler. Already we have discussed that it is also called as the short-term scheduler, or it is called as the CPU scheduler, right? So processes which are present in the ready queue out of suppose 10 process or 100 process here. So one process is to be taken from this particular queue and is to be selected and given to the processor for the execution, right? So it is the duty of the CPU scheduler to select the process and it is assigned to the processor. This is the first point. Now the second important point is that how this CPU scheduler, see carefully, how the CPU scheduler select the process out of 10 process, how one process is to be selected and it is given to the processor for its execution, right? So if there may be question, for example, if there are 60 students in TIT class, right? So out of 60 students, if we want to elect or if we want to select one CR, that is class representative, or one LR, that is ladies representative, then out of 30 girls and out of 30 boys, to whom is to be selected as a CR and LR? That is a big question. So what we have to do here, because all are equal, all are in third year, all are sitting in the same class. Okay, so which criteria? So we have to apply certain criteria, we have to apply certain logic, or we have to follow certain algorithm here. So meaning is that selection, when there is a selection is involved, then we have to apply some decision making algorithm. Getting my point or not? Decision making algorithm means what? If the 10 processes here, 1, 2, 3, 4, 5, up to 10 processes are here ready. So suppose I can select, I in the sense CPU scheduler can select first process, or it can select second process, or it may select the 10th process first for the execution. Right? So then how it is going to select the 10th process first or 7th process first, and then when it can get the 5th process, then it can go for the 3rd process. It may happen. So this is nothing but the decision making which is carried out by that particular CPU scheduler. And if the decision making is there, definitely we have to follow, or you have to follow the algorithms, right? So there are 4 algorithms, that is first come first serve. So here CPU scheduler either apply the FCFS policy or FCFS strategy. Means it will just go for the process which is first enter into the queue, that will assign first to the CPU for the execution. Very simplest criteria. See carefully, yeah? The processes which are placed here, suppose there are 10 processes, they are in a ready queue. Now it is the duty of the CPU scheduler to select one process from this queue and assign it to the processor for the execution. Clear? So this is our main goal. Now out of the 10 processes, say for example, if the processor, if this particular CPU scheduler apply the FCFS criteria, means first come first serve, then the first process, the process which come first, it will be assigned CPU first for the execution. The process which is come second, that will be gets CPU for the second time for the second turn to its execution. Then third process will have the third number for the execution. The simplest criteria or the simplest logic. Or it may apply SJF, shortest job first. The CPU scheduler checks the execution time, or CPU scheduler has to see the execution time of each process. So it may happen that the execution time required for the first process is more as compared to execution time that is required for the second process. So process P1 having time required 10 milliseconds, but process P2, the total execution time required is only for 5 milliseconds. So why unnecessarily process P2 has to wait till the process P1 finish its complete execution? Are you getting my point or not? So here what SJ policy says that the process is to be selected having the shortest CPU burst time. Means the process is selected having the shortest CPU burst time or CPU execution time. Say for example process P2, only 5 milliseconds is required, so P2 is taken first and then P1 is taken for the execution after complete execution of the P2 process, because P2 require only 5 milliseconds and P1 require 10 milliseconds. So comparison is take place between the execution time or the CPU burst time. So that logic is to be applied by the CPU scheduler. Our third criteria is that it may go for the priority scheduling. There is a priority assigned to the processes, and depending upon the highest priority process, the process is taken from the ready queue and it is assigned to the CPU for the execution. Right? Or there may be a round robin policy. So there are different policies, there are different algorithms that are followed here by the CPU scheduler that we have to discuss in depth. How these algorithms work and what is exactly the output of this each and every algorithm, right? So before starting to the algorithms, so first we have to study the concept of preemptive scheduling and non-preemptive scheduling. So the CPU scheduler takes the decision under the following circumstances. So first and fourth is no choice for the CPU scheduler, that is no preemption. If this is the first one and this is the fourth one. So preemptive, non-preemptive scheduling and the preemptive scheduling we have to see. So preemption, the meaning of the preemption or non-preemption in the sense, once the CPU has been allocated to the process keep the CPU until its complete execution or until its complete termination. The meaning is that non-preemption, see here carefully, the meaning of non-preemption is that once the process is selected from the ready queue and it is assigned to the CPU and the process currently is in a running state. For example, P1 is selected and P1 is currently in a running state. Then the non-preemptive policy or non-preemptive scheduling says that this particular process will remain in the processor till its complete execution. So it will be removed. The process P1 will be removed from the processor only after its complete execution or only after its complete execution or the 100% execution of the process. Getting my point around? So non-preemption. So what is preemptive scheduling then? So preemptive scheduling in the sense that, say for example, process P1. Consider example, process P1. It is in a ready queue. Now it is selected and it is taken for the execution. So P1 currently in a running state. So processor is executing the process P1. So preemptive scheduling in the sense that if, for example, higher priority process comes here, if, for example, higher priority process comes here, then immediately the currently running process, see carefully, yeah, currently running process is to be removed from the processor and newly added process is taken in the processor for the execution. Getting this point? For example, say for example, in a casualty, the patients are, suppose I consider example of your hospital, casualty, the patients are there in a queue, and the doctor examining the patient in a queue, first, second, third, fourth. But it may happen that some severe case or accident case comes there. So definitely the doctor has to rush to that particular patient which has just arrived and having the accident case. So that patient is having the highest priority. So meaning is that the patient which is currently in the doctor's cabin, it has to wait till the complete execution of the newly arrived patient or the process. So that is the meaning of preemption. So again, the concept is that preemption in the sense that the process will be preempted. The process currently executing process will be preempted when the newly arrived process is having the highest priority or the maximum priority, right? So the process completes the 50% execution, and at the time it may happen that the new process arrive having the highest priority, right? So this process will be removed from the processor and it is again placed back into the ready queue, right? And the newly added process is assigns processor for its execution. Getting my point or not? Then after completion of that particular process, which is newly added process, it will be terminated as soon as its execution is complete. Then only the previous process. So 50% execution was complete in the first stage, and the remaining 50% execution will be completed in the second stage. That is called as the preemptive scheduling. And non-preemptive scheduling in the sense that once the CPU has been allocated to the process, so whatever it may be, then the process will be kept in the CPU till its complete execution. Getting this point or not? So this is the way. Preemptive scheduling in the sense the running process may be replaced by a higher priority process at any time. At any time. So this is the one. Running process may be replaced by the higher priority process at any time. Getting this point? Meaning is that the newly arrived process is having the highest priority. So the first process P1 is to be removed from the processor and it is taken back in the ready queue, and the currently arrived process will be execute successful. Getting this point? So this is the difference between the preemptive scheduling and the non-preemptive scheduling. And these criteria which we are going to discuss, that is scheduling criteria, they may be of the type of preemptive scheduling or they may be of the type of non-preemptive scheduling. So clear the concept. Non-preemptive means once the CPU has been allocated to the process, it will completely execute. It will not be removed from the processor until its complete execution. That is, so whatever it may be, whether the higher priority process comes or not, the process will complete its execution. That is called as the non-preemption. See carefully and understand the concept carefully, because all the next algorithms, they are depend on this concept only. Preemptive type of scheduling or non-preemptive type of scheduling, right? So if you have the doubt, you can ask, right? Now the scheduling criteria, we'll see the next point, that is nothing but the scheduling criteria. So criteria in the sense, the algorithms which we are going to discuss, that is FCFS or HJF or round robin or priority scheduling, so they must fulfill the criteria. That is nothing but the CPU utilization is the first criteria. Second criteria is nothing but the throughput. The third criteria is nothing but the turnaround time and the waiting time and the response time. Now see the concept carefully, listen it carefully, try to understand it carefully. CPU utilization, the algorithm, the CPU scheduling algorithm, they are such a efficient that they must be such a efficient that they must increase your CPU utilization. Meaning is that your CPU must be busy for all the time, right? So there must be 100% utilization of your CPU. So meaning is that the algorithm must give the result 100% CPU utilization, or CPU, that particular algorithm must be so efficient that we can have the 100% or maximum CPU utilization. CPU utilization means what? The ratio, that is nothing but we have to keep the CPU busy as much as possible, because CPU is one resource. CPU is one resource and it is a very important resource. It is a crucial one, right? So it is not affordable to let the CPU remains as it is without having any process for the execution. Means it must not sit idle for a single millisecond of time. So CPU must be busy in executing the processes all the time. So that is nothing but we are utilizing our CPU up to 100% capacity. Next point, throughput. Throughput is nothing but your number of processes that are completed per unit time. That is nothing but your, one can say that it is nothing but the ratio to your input to the output, right? So here I can able to draw, say for example, input to output ratio. So here, for example, 5 processes are input and I can have the 5 process output. Means I can have the 100% throughput from that particular system. Ratio, input to output ratio, right? Turnaround time. Turnaround time is nothing but the interval from time of submission of the process to the time of completion of the process. Means it is nothing but when you, so again if we consider the diagram, that is our process state diagram. Say for example your new state, then your ready state, then your running state here, and this is the termination state, and this is your waiting state. So this one, so see these two lines. So when you submit the process into the system, and when the process leaves from the system, so this total time is called as the turnaround time. When the newly process is created and it is placed inside the ready queue, then from the ready state it is taken inside the processor for execution. So it has to wait here, it has to wait in the ready queue, and here is nothing but the execution time. CPU time is nothing but it is called as the execution time is E. So waiting time plus execution time. So the time spent by the process in a waiting queue, in a ready queue, right? The time spent by the process with the processor, that is at actual execution time of the process, and the time spent by the process in waiting here. Suppose in device, suppose it is waiting for a certain device to get. So addition of this waiting time plus this waiting time plus this execution time. So total time between this interval, this is the input and output interval. This is the input one, this is the input, and this is, one can say, this is the output. So total interval time, it is called as the waiting time for that turnaround time for the, turnaround time. That is the waiting time to get into the memory, waiting time in a ready queue, and the actual execution time in the CPU. Clear this point or not? Turnaround time is nothing but the addition of your waiting time in the memory, means this waiting time, the waiting time in the ready queue, and the execution time. So this waiting time also there, and execution. The total time spent by the process during its lifetime, it is called as the turnaround time. Then what is the waiting? So waiting time is the sum of the periods spent in waiting in the ready queue. This is the time only called as the waiting time. The time spent by the process in a ready queue. This one is the ready queue. That is called as the actual waiting time. And the response time is nothing but the time from submission of a request until the first response is get, right? Just I want to clear this. Okay. So this is nothing but the concept of the turnaround time and the waiting time and the response time. Clear, all of you? Okay. So just revise the concept. Preemptive scheduling. Once the running process may be preempted by the higher priority process at any time. That is nothing but the preemption. And non-preemption means what? The process, once it has been assigned to the CPU. Say for example in CPU, the process currently in a running state, it will not be removed. It will not be removed from the processor till its complete execution. Right? Okay. Now see the next one. Now this is the first scheduling algorithm, that is called as the first come first serve, or it is called as the FCFS algorithm. The very simplest strategy, CPU scheduling algorithm, the first come first serve, the simplest scheduling algorithm, easy to implement and easy to understand. Clear this one? Easy to implement and easy to understand. CPU is allocated to the process and it is a non-preemptive type. Always remember, this is a non-preemptive type. Non-preemptive type means what? When you are following FCFS policy, right, and when you are following the FCFS one, and once the process has been given into the CPU, once the process has been allocated to the CPU, say for example this is your processor and process P1 currently in a running state, then the process will be completely executed. The process will remove from the processor after its complete execution. After its complete execution, the process P1 will be removed from the processor. right? This is nothing but your FCFS policy. And the second important point is that the CPU is allocated to the process in the order of arrival. As the processes are arrived, their order of arrival, the processes are selected and it is taken for the execution. This is the simple concept of this particular FCFS algorithm. Just like what we can say that just like your ticket counter. For example, you go to movie in cinema hall and to watch the movie cinema hall. So on a ticket counter, the customer who are first in the line, they get the first ticket, they get the first priority, and the customer who comes late, he may not get the ticket due to the houseful show. It may happen, right? So this is the very simplest strategy, simple to understand and simple to implement. Programmatically, we have to implement and see that all the algorithms. So one can say that all these particular algorithms we have to implement in at the time of practical assignment, right? So see here, consider see one example. It will make you more clear. Example: consider all the process arrival time is 0. Arrival time of the process is considered to be 0. Now, what is the arrival time of the process? That we have to see. Right. So arrival time of the process, for example, if I draw here for the simplicity, if I draw, this is the time axis, for example, this is the t here, right? And say for example 0, right? This is the 0, and this is say for example 10 o'clock. This is the 10 o'clock, and this is say for example 10 o'clock, right? And OS lecture started. OS lecture start, right? So we can say that initially at 0 means at 10 o'clock, exactly at 10 o'clock, OS lecture has been started, and initially, say for example, 30 students were present at 10 o'clock in the classroom, and when I entered in the class and when I starting delivering the lecture, how many students are present in the class? The 30 students were already present. Now, after 5 minutes, say for example 10, after 5 minutes, that is nothing but your 10.05. After 5 minutes, say for example, the 5 students came into the class. They get late. It is generally habit of the student. They do not reach to the class on time. Generally, we have this habit in our department or in our college. The student they used to come late during the period time, right? So 5 is the less number, but there are more students. But let it be. So we assume that 5 students they came late at 10.05 after 5 minutes when the actual lecture has been started, right? And it may happen that some student after 10 milliseconds, sorry, after 10 minutes, so again 5 students came into the class, right? So see, so here arrival time, we are discussing the concept of arrival time. So arrival time in the sense, the arrival time, so initially when the lecture is started, say for example the 0th instance means 10 o'clock, for example. 0th instance means the 10 o'clock. When the lecture has been started at 10 o'clock means 0th millisecond, how many students were present? The 30 students were actually present, and they are start attending their lectures. Now after 5 minutes, the 5 students enters into the classroom, and again after 5 minutes mean 10.05, 5 students means total strength becomes now 35, and here after again 5 minutes means total 10, after 10 minutes again 5 students come, so total strength of the students now becomes here 40, right? Now suppose the lecture completed at say for example 11 o'clock. Suppose it is a 1 hour lecture, for example, right? So what is the effective time spent by the students in the classroom? That is nothing but the concept of arrival time, right? See carefully, the students who were present initially starting from lecture, 30 students, how much time they have spent in the classroom up to 11 o'clock? Exactly 1 hour, they have spent here, or exactly 60 minutes they have spent here, right? 60 minutes spent by the 30, because their arrival time is 0. Arrival time is 0. So what is the waiting time of these 30 students? So waiting time in this classroom 0 to 11 or 0 to 60 minutes. The waiting time for initial 30 students is 60 minutes. Clear? Now waiting time for the next 5 students, the students who were joined 5 minutes late. So what exactly is the waiting? So these 5 students, how much time they spend in the classroom? They spend only 55 minutes in the classroom, means they effectively attended the lecture for only for 55 minutes, because they were late. Their arrival time is 5 minutes, for example 5 milliseconds. Getting this point? And the remaining 5 students, their arrival time is 10 minutes, or sorry 10 milliseconds. So how many minutes they were actually present in the lecture? So they were actually present for 50 minutes effective they have attended the lectures. So clear all of you. So when we say that arrival time of the process, so when the actual, so here again the same diagram, this is 0 and say for example this is t, when the process starts its execution, when the process started its execution, when the system started, and say for example at 0th instant, say for example P1 is present, then P2 is present, and P3 is present in the system. So arrival time of these three processes is 0 millisecond. But after 5 milliseconds, suppose P4 process arrive, its arrival time is considered to be 5, and it must be subtracted from the execution time, or it may be subtracted from the waiting time for that particular process. Because 0 to 5 it is not present. From 0 to 5 millisecond, the process was absent or it is not at all present. So what exactly is the waiting time for this 5? So from it is for process P4, it is to be considered from this 5th millisecond and onwards. It is to be considered from 5th millisecond and onwards here, similar to our students. So effective waiting time for these students who were at come after 10 minutes, that is this 0 to 10, it is not calculated here. So 60 minus 10, 60, this is the 60 minus initial 10, that is actual only 50 minutes is the waiting time for this 5 student. And same for this 5 student, the 60 minus 5, that is the 55 minutes. Actually, this is their waiting time. For this student, this is the only 50 minutes waiting time for this particular student. Getting the concept of arrival time. So arrival time, remember this point, because students generally every year I explain this concept very well, but the students they get confused while calculating the arrival time and while considering the execution time and waiting time of the process. So arrival time is the very important concept, right? Just let me clear this thing. Okay, so same example. So here I can say there one more column I add here. So arrival time. So the handwriting is not so much good here. Arrival time, right? So arrival time is 0 for the process P1. It is again for 0. It is for 0 and it is for 0. So consider there are 4 processes: process P1, process P2, process P3, and process P4. And their execution time. Burst time is called as the execution time or the CPU burst time. The 3 millisecond, 6 millisecond, 4 millisecond, and 2 millisecond. And arrival time for all the processes 0, 0, 0 means all the process. So here again I draw the diagram again here. So when I started, when operating system start execution, so at 0th millisecond on timing diagram 0 to t, for example. So all the processes are present here. So P1 is available, P2 is available here, then P3 is also present here. Right, and P4 is present at the 0th millisecond, and P1 is required 3 millisecond, P2 requires 6 millisecond, P3 requires 4 millisecond, and P4 requires 2 milliseconds here, right? So now FCFS policy. So what is the logic of FCFS? FCFS says that the CPU is allocated to the process in the arrival order, right? So what is the arrival order? So P1 comes first, so definitely it will go first for the execution. P2 comes second, so it will go for second. P3 third, and P4 go for the fourth at the fourth, right? So first P1 is taken and the execution time is 3 milliseconds from 0 to 3. So P1 process is executed here. This is the P1 process, right? Then at 3 milliseconds, sorry, this is the 3. So at 3 milliseconds, the execution of P1 is completely done. At 3 milliseconds, the execution of P1 is completely done. So as soon as the P1 process get executed, it will be removed. It will be removed from that particular. It will be removed from that particular system, right? Then process P2 is taken for the as soon as the execution completes here. As soon as the execution of the process P1 complete, so P2 is taken for the execution. And how much time P2 spends here? So P2 requires 6 milliseconds. So 3 plus 6, that is equal to 9. So 6 milliseconds P2 is taken. So this is nothing but the execution time for the process P2. This is the execution time for the process P3. Sorry, P1. So P1 is 3 milliseconds, P2 is for 6 milliseconds, and P3 requires 4 milliseconds. So 9 plus 4, so 13. So this is nothing but your P3 process is taken for the execution. So it will be executed completely up to 4 milliseconds, and as soon as it will be executed, it will be removed and it will be terminated, right? And then P4 is taken for the execution, and P4 require only how much milliseconds? It requires only 15 milliseconds here, right? So this is nothing but your P4. So this is the way, and this is called as the gantt. So see here, it may not be clear. But here this is very well created or very well drawn here. So 0 to 3, 3 to 9, 9 to 13, and 13 to 15. So P1 takes only 3 milliseconds, P2 takes here 6 milliseconds, and P3 takes here now 9 to 13 means 4 milliseconds, and from 13 to 15 the 2 milliseconds. Right. Now then we have to draw here. We have to find out the waiting time for the process P1. Waiting time means how much time the process wait before it get the CPU for the execution. Waiting time in the sense that we have to find out the waiting time for the process before it gets the CPU for the execution. So P1, how much time P1 has to wait here? So P1 is 0, it is available at 0 and immediately it is taken for the execution. So waiting time is 0 millisecond only. Now for P2, so P2 has to wait up to execution of the first process P1 3 milliseconds. So waiting time is 3 milliseconds. P3, so P3 started this execution here from 9. So waiting time is 9 milliseconds. And P4, so P4 has to wait till the complete execution of P1, P2, P3. That is up to 30 milliseconds. P4 has to wait. So P4 waiting time for P4 is 13 milliseconds. Right? So we will just find out the average waiting time for all the process 0, 3, 9, and 13. That is divided by 4. That is equal to 25 by 4. The AWT. This is called as the AWT, average waiting time for all the process. AWT is 6.25. Getting this point? So waiting time for each process we are collecting P1, P2, P3, and P4, and we are finally finding out the average waiting time for the process. Now, after finding out the waiting time for the process, we have to find out the turnaround time. Now, turnaround time is nothing but the addition of the burst time or the execution time at the waiting time. So just write down here P1, P2, P3, and P4, and the burst time is 3, 6, 6, 4, and 2. 3, 6, 4, 2. And what is the waiting time for process P1? It is 0 millisecond. Waiting time for process P2 is the 3 millisecond. For P3 it is 9, and for P4 it is 13 milliseconds. So this is nothing but the turnaround time for each process. P1 turnaround time is 3. For P2 turnaround time is waiting plus burst time, that is 9. For P3 it is 4 plus 9 equal to 13, and for P4 it is 2 plus 13, that is equal to 15 milliseconds. So we are going to again add up this thing, 9, 3, 9, 13, 15 divided by 4. So this is 10 milliseconds. This is nothing but the average turnaround time of the processes. Getting this point? So this is the one can say this one is nothing but your simplest strategy, that is called as the first come first serve, where the processes are assigned the CPU as per their arrival of order and arrival time, and this is the non-preemptive policy. FCFS, once the processor has been allocated, the process will completely execute, and then only it will remove from the processor, right? So waiting time, and we have to calculate the waiting time like this: 0. Then waiting time for P2 is 3, for P3 is 9, and for P4 is 13. We have to find out the average, and again we have to find out average waiting time, AWT and ATT. And this is the simplest algorithm, that is called as a first come first serve, right? And AWT. So so there is a question always numerical asked in the examination. We have to draw the Gantt chart. This particular diagram is called as the Gantt chart. We have to draw the Gantt chart for that particular set of processes. The first step. The second step is that we have to find out the waiting time for each and every process. The third step is that we have to find out the average waiting time for each process. The fourth step is nothing but we have to find out the turnaround time for each process. And finally, we have to add all these average time and we have to find out the average waiting time for the process. And the logic is the first come first serve, the arrival order we have to consider here, right? And we are finding out this thing. Okay. Now the next scheduling algorithm. So we'll go to the next one, and that is called as the SJF, shortest job scheduling. It is also called as the shortest next CPU burst algorithm. So this algorithm associates with the length of the next CPU burst. Meaning is that here, instead of arrival time as in the previous algorithm, here it considers the execution time of the process. So depending upon the execution time, it will take the process for the execution. The first criteria. And the second criteria is that it is either preemptive or either non-preemptive. Right? So preemptive means what? A preemptive SJF. So here the two conditions we have to apply. First is the SJF and second is the preemptive. So conditions tell that preemptive SJF will preempt currently executing process whereas non-preemptive SJF allows currently running process to complete finish its CPU burst. Right. It is optimal as it gives minimum average waiting time. So this algorithm, as compared to the all the four algorithm, this algorithm gives us minimum average waiting time and minimum average turnaround time. It is mostly used in the long-term scheduler, right? So again consider the same example, processes P1, P2, P3, P4 and their execution time is 3, 6, 4, 2 and arrival time is 0. Arrival time is given is equal to 0. So out of this 3, 6, 4, 2, which process is having the shortest execution time? The process P2 having the shortest execution time, then comes the process P1, then comes the process P3 and then comes the process P2. This is the sequence. So we have to first execute the process P4 first because it is having the shortest execution time 2 milliseconds, right? Then we have to go for the process P1 because it has again having the shortest execution time. Then the process P3 and finally we can go for the process P2 depending upon the execution time of the process. Right? This is the strategy. This is algorithm is the shortest job scheduling or the SJF shortest job first. The process having minimum execution time that is taken first for the execution. Clear this one. Now here important point is to be remember that arrival time of all the process are here 0. Meaning is that all processes are present at the 0th time instance. When the system is actually started, all process P1, P2, P3, P4 are present here with their execution time or with their CPU burst time. So you have the chance for the comparison. You can compare between all these four processes, and by comparing you can find that yes, the P4 is having the shortest one, so P4 will go first for the execution, then P1 will go, then P3 will go, and then P2 will go for the execution. So why this is possible? Because all processes are present at arrival time 0, right? But it may happen that after 5 milliseconds, one process comes, for example, P5 process, and it has only 1 millisecond of execution time. Getting my point or not? After 5 milliseconds, one process, next process, new process arrived in the system, that is called as the P5 process, and if the execution time is equal to 1 millisecond, then what to do here? So up to 5 milliseconds, if we draw the diagram again, Gantt chart, 0 to 5, there is no question of this thing because after 5 milliseconds, this P5 enters into the system. So we have after 5 milliseconds, we have to compare this particular P5 process with the existing process. But at 0th millisecond, you cannot compare this P5 process because at 0th millisecond, it is not present. It is not available in the system. Getting this point or not? So for simplicity, we'll just first see this example. So processes 3, 6, 4, 2. Just draw the Gantt chart again. So first process is 0, and it is the first process is nothing but your P4 process. It is taken for the execution, and the time required is equal to 2 milliseconds from 0 to 2, for example. Then the next process is 3 milliseconds required, that is called as the P1 process, and P1 process required 3 minutes, 2 plus 3 is equal to 5. Then next is nothing but your P3 process. So P3 is taken for the execution, and the time required is 4. So 4 plus 5 is equal to 9. And finally, the final is nothing but your P2 requires 6. So 9 plus 6 is equal to 15. And here is nothing but your P2 process. So this one is nothing but, so I can draw the Gantt chart like this. First I have to draw the x-axis, and then I have to draw the, I can write here 0 to that is nothing but the actual execution time of each process, and then I can mark this square or this rectangle, and the Gantt chart is complete. So this is the first step to draw the Gantt chart for this particular set of processes. Right now, from this Gantt chart, if the Gantt chart is correct, then your waiting time and turnaround time will be correct. But if you do the mistake in the drawing Gantt chart, then the rest of your answer will be wrong here. So while drawing the Gantt chart, we have to carefully see the arrival time as well as the execution time of each and every process. Right. So which is the first process which is taken for the execution? So so for finding out the waiting time, again waiting time for P1. Now see here, when process P1 is taken for the execution. So P1 is taken for the execution at the second millisecond or at the 2 milliseconds. So we can say that 0 to 2. 0 to 2 is the waiting time for the process P1. Right. Then, so waiting time for P1 is 2. Then for P2, the waiting time is 9. Why 9? Because P2 is taken from here, and it will be executed during this slot, 9 to 15 slot. So 0 to 9, this particular millisecond that P2 has to wait here. P2 is waiting to get the CPU because here it gets the CPU for the execution. right? Then for P3 is time is equal to 5 milliseconds. Why 5? Because it has to wait from 0 to 5 milliseconds, and after 5 milliseconds, P3 get the CPU, and this time 5 to 9 is actually the execution time of the process. This is the execution time, and this is the waiting time for the P3 process, right? And for P4 do not have to wait here, because P4 immediately when you start your system at 0th millisecond, the P4 immediately it is taken for the execution. So there is a 0 waiting time for the process P4. So we just add all this waiting time, 2 plus 9 plus 5 plus 0, that is equal to, divided by 4, that is equal to 4 milliseconds is the average waiting time. This is called as the AWT. Turnaround time is nothing but the addition of your waiting time, and it is nothing but the burst time or the execution time. So you can have 3 plus 2 5, then 6 plus 9 is equal to 15, then 4 plus 5 is equal to 9, and 2 plus 0 is equal to 2. So total turnaround time, the average turnaround time is calculated by adding this thing, 5 plus 15 plus 9 plus 2 divided by 4, that is equal to 31 by 4, that is equal to 7.75. It is called as the average turnaround time. So see, this is the same set of process or same example that we have discussed earlier with the FCFS. So FCFS gives you the more waiting time as well as the more turnaround time, but here you get here minimum average waiting time and the minimum average turnaround time, right? So this is the second algorithm, that is called as the shortest job first, where we are going to consider the execution time of the process. Here we are going to consider the execution time, or the second column we are going to consider here. And arrival time, of course, we are also going to consider the arrival time, because all the processes, they are arrived at the 0th time instance. They are arrived at the 0th time instance. Clear? Okay. Now the next algorithm, or the third algorithm, is priority scheduling. Now the priority scheduling meaning is that each and every process has been assigned some priority. Means priority P1 having certain priority is equal to 1, then P2 having, say for example, priority 3, then P3 is having priority 5, then P4 is having priority 2. So the lowest number of the priority indicates the highest priority. Lowest number indicates the highest priority. So 1, 2, 3 and 5. So the processes, so here we are not going to consider this column, we are not going to consider the execution time, but rather than we are going to consider the priority of the process, right? What is the priority of the process? So lowest is the number, highest is the priority. So CPU is allocated to the highest priority of the process from ready queue. So and if there is a priority, equal priority, if the equal priority, then it is called as the FCFS. Then it again go for the FCFS policy. Low number or the lowest number indicates the highest priority. The number 1 is the highest priority as compared to number 9. If the 9 is there, 9 has to come later on, right? So it may be either preemptive or it may be either non-preemptive. Preemptive in the sense that suppose there are two processes. Suppose P1 is there, P1 having the 5 number priority, and P2 is having equal to 2 number priority. So 2 is less. But currently P1 is currently in a running state. For example, P1 is currently in a execution state. Then when as soon as P2 arrives, so immediately this P1 process is removed from the processor and P2 will be assigned processor for its execution, because P2 is having the highest priority. P2 is having the highest priority, and it is the preemptive one. Preemptive means you are going to remove the currently executing process and assign the processor to the newly added process, right? So this is the way, means in a simple word we can say that here we are going to consider the priority of the process and not the execution time of the process. So see one example. From this here it is clear that process P1 execution time is equal to 10 and the priority assigned is equal to 3. Process P2 execution time is equal to 1 and priority is equal to 1. Process P3 execution time is equal to 2 and priority is equal to 3. Process P4 execution time is 1 and priority is equal to 4, and P5 execution time is 5 and priority is 2. So start drawing the Gantt chart here. 0 for example. So which is having the highest priority? So this column we are not going to consider here, right? We are going to consider the priority of the process. So out of this 1, 2, 3, 4, 5, this one first is having, this is P2 is having the highest priority, number 1. So P2 is taken first for the execution, and it will, how much it will execute? It will execute only for 1 millisecond. It will execute for 1 millisecond, right? Then the priority is equal to having process P5 having priority 2 and execution time is equal to 5. So from 1 to 5 milliseconds means it will take total up to 6. So this is nothing but your P5 process. Right. The next priority is P1 and P3. They are having equal priority. Equal priority means 3-3. So if the priorities are equal priority, then you have to go for the FCFS one, right? So FCFS means P1 comes first as compared to P3. So then go for the P1. So I take here P1 for the execution, and P1, how much is the execution time is 10. So 10 plus 6 equal to 16, and then go for the P3. That is equal to P3 if it is execution time is 2. That is nothing but 18. And the remaining process is nothing but P4. Finally, the P4 is taken for the execution. So 18 plus 1 is equal to 19. So this is actually the Gantt chart for the process, this particular set of processes. So waiting time for each process. So first step is completed. We have drawn the Gantt chart here. The waiting time for process P1. So P1, where is the P1? So P1 start execution here. This is the execution time for the P1. That is from 6 to 16. Execution time is 10 milliseconds. But up to 0 to 6, this is nothing but the waiting time for process P1. Right? So this is waiting time for process P1. Now for P2, P2 does not have to wait here, because immediately when the system is started, the P2 is taken for the execution. So waiting time is equal to 0. Right? Then process P3. P3 is started execution from here. That is nothing but your 16, from 16. So 0 to 16, this much time, this is nothing but the waiting time for the process P3. Then for process P4. So P4 is started execution from 18. So you can have 0 to 18 is nothing but the waiting time. And for P5 is actually started execution here, and it will complete execute here. So we can have 1 millisecond is the waiting time for the P5 process, right? So we can add up all this, and we can find out the average waiting time. So average waiting time for the setup system is 8.2 millisecond, right? And turnaround time is nothing but your execution time plus waiting time, and we are finding out the turnaround time for P1, P2, P3, P4, and P5. Add up all these things, and we are getting here the average turnaround time. This is nothing but average turnaround time and average waiting time, right? So that's all about these three algorithms. So next algorithm is the round robin scheduling. But for this round robin scheduling, so I suggest that the all students, they must accompany with their notebook and pen. We will solve the examples on your notebook, because from the slides I think it may not be very clear to you, and we will see this round robin algorithm in the next lecture.